What's up, YouTube? Today we are going to be doing some more numerical methods analysis, and we're going to be looking at the LU decomposition of a given matrix, a square matrix. So keep that in mind. It's always going to be square when using the LU decomposition. So basically, what is LU decomposition? If we're given a matrix A, we want to say, okay, let's split it up into the product of two matrices. L being the lower matrix and U being the upper matrix. So what does that even mean? Okay, so we look at the L, the lower triangular matrix. One interesting characteristic is that all the diagonals are equal to 1, the diagonal components, and the upper components are all zeros. Right, so then the lower triangular portion is our matrix values, right? So now what is a upper triangular matrix? It's literally just the opposite, except for our diagonals are not equal to 1. They were our actual values as well. Okay, so these are the breakdown of our lower triangular matrix and our upper triangular matrix. And now the product of these two matrices has to equal our original given matrix A. And the given matrix A is up here. We have 1, 5, 0, 0, 2, 12, 5, 0, 0, 4, 13, 5, 0, 0, 6, 11. So this was actually a example, a question from a past midterm. So it's kind of tricky, but it's actually easy if you understand the process. So when we're solving for the upper and lower triangular matrices, we want to start out by just labeling our lower triangular matrix, and then our upper triangular matrix is what we're going to be using to solve for each individual component of our lower triangular matrix. So given the matrix A. Okay, so how to start these problems? First things first, you want to look at your given matrix A, and what you want to do, you want to reduce using row operations, and reduce it to the form of an upper triangular matrix. Okay, and that's how we solve the upper triangular matrix. And I'll show you how to now then solve in for each component of the lower triangular matrix. You can do them together. So looking at our first component that we want to eliminate, we have this 2 here, right? So we want to eliminate this 2 using row operators. So how would we do that? We would row 2, and we would add minus 2 times row 1. Right, because we have a 1 in this component, and then to eliminate this component, we just add the negative 2 times the 1, and that'll give us a 0, right? So this gives us top row remains unchanged, and now we have a 0, and 12 plus negative 10 gives us 2, 5, 0. And the other rows remain unchanged. So now we had a row operator, this row operation here, right? And now we can now start filling in our lower triangular matrix by looking at our factor. Our factor was negative 2, right? The negative 2 times row 1 canceled out our component in the first column of the second row. So then we need to just put in since we canceled out the first column, second row, we take the factor that we used to cancel out that value, and we put it in the same slot that we just got a 0. So the opposite of negative 2 is positive 2. So we put the positive 2 in the same slot that we used this factor to cancel out that value. And we do that for each value in our original matrix and plug in the opposite sign of that same factor. So let's do that again. Okay, so now we're looking at this 4. We want to cancel out this 4, right? So how would we do that? Looking at our new matrix, we have the 4, and we can see that it's 2 times the second column in our second row. So that's easy. So we take R3, add -2 times R2. First row remains unchanged. Second row remains unchanged. And now the third row, 4 plus -2 times 2 is 0. 13 plus -5 times 2 is 3. 5 is 0, and then the third row remains unchanged. Okay, so then same thing that we did on the last factor. This is a coincidence, but the factor is also -2, adding to this slot. So the second column, third row. So we go to the second column, third row, and we put in that same factor but opposite signs. So then we have a 2 again. So keep in mind that these don't always have to be the same. Just in this particular example, they both happen to be -2 for the factors. This is likely because this is an exam question, and that was kind of used to save time. I guess it would just be an easier marking scheme for the teacher. But in this case, these 2's are the same, but they don't always have to be the same. It's just this particular example that it's a coincidence. Okay, so now looking at our new matrix, we want to get rid of this guy. Similarly, we just add -2 times that row. So we have R4 plus, again, -2 times R3, and that will cancel out that 6. So let's write out this new matrix. So after performing that matrix operator, we get 1, 5, and these remain unchanged. Oops, this should be a 5. Wrote down a 0 by accident. So 0, 0, and then 6 -2 times -3 is 0. And then we have 11 plus -2 times 5 equals 1. Okay, so now looking back at our lower triangular matrix, we've got another factor of 2. Okay, so we had our -2 times R3, which is our factor for canceling out the 4th row, 3rd column. So then we look here at our lower triangular matrix, and that same slot, 4th row, 3rd column, we put in the same factor, opposite sign. Okay, so then we have 2, 2, and 2. Those are all of our factors, which is 2, 2, and 2. So that's how you fill in your lower triangular matrix. And in this case, the rest of our matrix is 0, so there's going to be no factor for those. But if there was a value there, we would just perform the exact same type of matrix operator to cancel out and get zeros for those components, and then put the opposite sign of that factor in our lower triangular matrix. So we found our lower triangular matrix, and then also this actually equals our upper triangular matrix, because if you notice, we have a 0, 0, 0, 0, and a 0, and another 0. So then this actually is the exact same as our form for our upper triangular matrix, right? We have all of our zeros, and then our values all in the upper triangular of our matrix. So now we've actually solved for the lower triangular matrix and the upper triangular matrix. So let's just write this out. So our lower triangular matrix was nothing more than and our upper triangular matrix. Lower and upper. And then just to confirm, you can do this on your own. We can show that our matrix A, our original matrix A, if you want to perform the entire matrix multiplication of these lower and upper matrix, you will actually get our original matrix that we started with, A. So perform this on your own, the matrix multiplication, and disprove to yourself that this product of the lower and upper triangular matrix actually equals the original matrix that we started with. So this type of operation is really useful for solving for the inverse of a matrix. I'll do that in a separate video. It would take too long to do in this video, but this basically is a really useful tool to use in MATLAB or any other operations. It kind of simplifies the process, your inverse of a matrix. So thanks for watching. If you like my video, check out my website at everythingeng.com and like and subscribe to my videos. Thanks for watching.